Okay, can you see my screen?
Yes.
Okay, let me put in. Just a second. Okay, I think I need to go to full screen. Okay, I cannot see, okay, I can still see you. So thanks for coming. Sorry, apologize in advance. I cannot stay until the end. The time zone doesn't help me. So I'm here today on behalf of the Chinese Academy of Science, my institute, Shanghai Astronomical Observatory, and also on behalf of the Cosmostatistics Initiative, which is a group that I created in 2014. And we have been doing a lot of interdisciplinary work since then. So I'm just going to give you a more or less overview what we have been doing. And then what I have done in the past years, and by the end of the talk, I'm going to talk a bit about the Chinese space mission and maybe opportunities also for collaboration. So I invite you to, in case you don't know about COIN, I just invite you to visit our website. You can see there will be a plenty of different projects there, and anyone's actually welcome to contact us and start any collaboration. So what COIN is and how we work. So basically, we are a group of researchers from all over the world. By now, we have around 70 researchers from 25 countries. And we have people from many different fields, mostly astronomers, but we have statisticians, computer scientists, musicians, philosophers. And the main goal is actually to try to put some effort in solve problems, and that's broadly defined. So every year we decide some particular project to attack, and then we try to bring the experts in particular fields together in the way that we can basically solve that. We have been actually starting partnerships also with other collaborators, including LSST Desk. I'm going to briefly talk about that. And about the subjects, mostly if you look at the papers we have been publishing in the past years, the topics, they vary more or less they go from nuclear astrophysics, deep learning for galaxy analysis, applications to medicine as well, extragalactic astrophysics, galactic astrophysics, open clusters, and so on, development in machine learning, cosmology, and also very foundational statistics. So I don't like names in any case, but people like sometimes to put this sort of thing under the umbrella, what people call astrostatistics, which is again is a loosely defined name, but let's say the key aspect of this brand is the attempt to try to customize some statistical methodology for a particular problem. It's not really about using a fancy analysis just for the sake of being fancy, but in my view, it's more about not to disentangle the physical model from the statistical model. And for, using this philosophy, one of the projects I have been working in the past years is actually to develop a Bayesian framework for nuclear astrophysics, specifically to probe and make inference of the reaction rates of the Big Bang nuclear synthesis. And then you may ask, why do we need that? Because basically, we have 12 reactions that happen in the Big Bang, but of course, we cannot recreate in laboratory the Big Bang conditions. So the best one can do is to create something that resembles the primordial plasma. But then there will be a lot of systematics and uncertainties that you need to put on top of the theoretical model to actually to be able to make the inference of the rates with a better accuracy. So in a certain sense, in my personal view, I think the statistics comes to kind of safeguard the theory to prevent you to actually to make the wrong assumption that the theory may be wrong just because it doesn't fit the data. So the statistics actually provides a way to communicate to the data to be sure if something actually is mismatching is not about your systematics, but most likely, sorry, not about your theory, but most likely about some particular instrument effect. So, and then following this logic, I have been publishing in series some reaction rates for the Big Bang, and they are actually included in abundance codes, and ultimately they are already used in Planck for estimates of the nuclear abundances. So just finishing about the overview, as I said, we have partnership with other collaborators. So one of them is between COIN and LSST Dark Energy Survey. We are basically developing a pipeline to do cosmology photometrically classify supernova. So in very short, for people that are not from the field, supernova is a particular type of stellar explosion that helps to probe dark energy. But to have an accurate distance to supernova, we need a spectra. Nevertheless, we cannot have a spectra for all supernova. So we have two choices. Either we just don't use the supernova that you only have photometry, but then we are going to throw away the largest amount of data because there are very few for which you can get spectra, or we can try to create some methodology that allow us to use the photometric classified supernova, but not making a lot of statistical mistakes. Okay, so about the review is over. So I'm going to give you one example of the project we have been working. And it's related to stellar clusters. Again, if you have no idea why we should care about stellar clusters, just think about every stellar cluster is a combination of stars that are born together. Because they are born together, they share similar properties. In other words, they give you a laboratory that you can probe and test your physical model of stellar formation and galactic formation and so on. So every time we discover a new open cluster or globular cluster or young stellar cluster, we are learning something about a particular snapshot of the universe. Okay, so as more as you can get this, better we can create a picture of the formation of the galaxy. And why we didn't discover all of them yet? Because it's very difficult to get the distances. So we are having actually a lot of new discoveries because of the Gaia satellite, which is a satellite from the European Space Agency that is providing unprecedented data about the Milky Way and the kinematic and astrometric information of stars. And because we are getting better data now, we are able actually to unreveal new types of these objects. So we have a systematic work in which we are actually probing and try to discover a few of these objects. There are different types, young ones, let's say the teenager ones, middle age, and then the very old ones. And each of them, they are useful for a particular thing. So the first project was about, let's say, the teenager and young adult stellar clusters, which is the so-called open clusters. So by just creating a model to try to find groups of stars that they have coherent in kinematics, or in other words, proper motion, basically, what an open cluster is in terms of data is a combination of stars that they have a coherent kinematics. And at the same time, they have a similar distance or parallax, and they have a particular behavior in what you call colored magnitude diagram, which basically provides a way to probe the distribution of stars. So by just doing that, we managed to find 45 new open clusters in the neighborhood region of the sun, which is already an increment of 20% of the previous population. So that's just to give an overview of how important new satellites and new data are when they provide better quality. So as a follow-up, we start to probe the young objects, which are, let's say, the ones that they probe closer to the region of star formation. Because the intuition is the following. The star is formed, but as the time passes, the stars moves away from the born place. If you find young stars and young clusters, you are getting the star formation very close to the place that the thing is happening. So this is a different animal to find because young objects, they are usually close to molecular clouds, and therefore there are a lot of dust. So we need to go to the near infrared, and then we combine data from Gaia and also Spitzer. But just the message to take home is we knew an example of a few of these objects, and we create a pipeline to try to seek similar objects based on the spectral, or in that case, the spectral energy distribution, right? And by doing so, we basically found 120,000 new young stellar object candidates. Now we actually got time on Palomar to get the spectra from the candidates to actually to test how robust our methodology are. So the plot I'm showing in the bottom is basically the map of the Milky Way in galactic coordinates. And this is the mid-galactic plan. And most of these objects, they are basically in the disk. So remember, when we find these objects, we are finding the regions of star formation. So we are probing the structure of the galaxy in regions in which we form stars. So the next step was to find clusters of these objects. And then this is another plot in real, like XY coordinates. And when I did the plot the first time, we noticed something coming out from the Sagittarius Arena arm, which immediately I considered that was a bug in the inference. So we tried to investigate further because we don't expect anything making a large angle related to the arm in principle. But then we went to the literature and actually we discovered that many galaxies, not the Milky Way, but many other galaxies, they actually show a similar structure. But we never saw that in the Milky Way before, just because we didn't have data. So we start to investigate, and we actually, again, we look at other galaxies to see what we call spurs. So basically, you have the spiral arms, and you have these basically spurs that they come out from the arms. There is no basically a clear model to explain that yet. So we don't know actually the orange, but we know these things exist and they are related to regions of star formation around the spiral arms. And then we customize a very robust statistical model for that to make sure we take account for measurement errors, outliers, everything. And by doing so, we got a few groups for which we have high accuracy in our estimate. And we end up actually publishing this. And this is the first evidence of a break, or let's say a spur in the galaxy. And this image is from a press release in Caltech. And actually, in the end, we end up getting a bit of fuzzy in the news. So this was the press release from NASA. And of course, because I'm in China, I managed to do the same in the Chinese Academy of Science. And also we got some other press release in German and other things. So I think the message here is the following. We wouldn't do that if you didn't customize the statistical model for this particular problem. On the other hand, just pure statistics without astronomical knowledge wouldn't do the same either. So I think the key point here that I would like to say is it was extremely important to collaborate with people from other fields. And I think that's what this workshop is about, right? I see in the same week a seminar about quantum gravity and stars and everything. So I think that's the key point that we try to follow in our group to provide synergy between different fields. So that's one of the results we have. And since I came to Shanghai, I started to get involved with the Chinese space mission. So that's something I'm bringing coin as well, but that's more related to my work here. And to give you intuition, basically, you can think as a upgrade. It's very similar to Hubble, but better because, of course, it's newer. So it's, let's say, a new generation of space telescopes that are going to have a broader wavelength and better images. So to give you an idea how important it is to go to space, for at least optical astronomy, I'm showing an 80-meter telescope, which is not a small thing, and also the image from 2-meter telescope in the sky, in the space, and you can see that the resolution is really far better. So the reason why it's the space station telescope is because they are going to launch in an orbit that's close to the Chinese space station. So if anything happens to the telescope, in principle, they should be able to fix because they are basically in the same orbit. We don't have exactly date, but we expect to launch in a year or two. But there are a lot of things that need to be decided. So I'm mostly involved in two of the instruments that are plenty. I don't know of them, but I'm mostly involved in the IFS, which is Integral Field Spectrograph, and the survey camera. And Shao specifically is developing the IFS instrument and also the multi-channel imager. Just to give you an idea and a comparison to the current missions. So this is the range of wavelength. The ones that are solid colors are basically the photometric bands, and the others are the spectroscopic coverage. And the field of view is far larger than Hubble. I'm showing a comparison here. So basically, the field of view is similar to 2 moons. And anyway, just for comparison, I'm showing Euclid, double first, and the Hubble Space Telescope. So the main survey is going to probe something around 17,500 square degrees, and expected to observe more than 1 billion galaxies up to magnitude 25. Again, that's just estimates, but probably around 100,000 strong gravitational lenses are going to be discovered, and then there will be spectra for something around 6 million galaxies. So that's challenging in terms of data analysis. Of course, we need to process 4.75 petaflops. There will be 30 petabytes of data over 10 years, and plenty of different types of data, spectral images, data cubes, and so on. So I'm going to give some 2 examples only about projects I'm started to develop with students here. So one of them is that because there will be plenty of different observations of galaxies, we need to find some kind of automated and still astronomic-driven way to classify these things. So we are just starting. So to get familiar with, we are using Sloan as a test bed, of course. And one of the first projects we are starting now is just to try to detect mergers and different merger, different stage of the merger. If it's a strong merger, a minor merger, if it's in the beginning, in the end. So for that, we are starting with something very traditional, just using convolutional neural nets as a starting point. But we actually plan to try to go beyond that and create actually a new paradigm to classify these things pixel-based. But just to give a sanity check of these preliminary results this is a list of new actually classified mergers. And we, of course, get random candidates to visually inspect. And many of them actually seems to be real mergers. And another sanity check we are doing is we have also a project to reconstruct the cosmic web. So the mergers should correlate more or less with large-scale structures because close to the filaments, you have higher density, and therefore we should expect more close interactions between galaxies. So if the classifier makes sense, it should see as an independent check some correlation with large-scale structures. And in the preliminary tests, we see some correlation. The red points are the merger candidates with a high probability, and the gray points that are more uniform are everything. So in a certain way, I think the preliminary results are promising. And just to finalize the second example, as I told you about the IFS, which is Integral Field Spectrograph, is also known in computer science as hyperspectral data, which means I have a tensor. It's basically tensorial data for people more familiar with this. So we need to basically get each pixel is a spectrum, which means we have spatial information about a particular galaxy, but also with spectral information. And there are plenty of problems to handle with this data because sometimes it's noisy, and if you try to run a particular code for spectral fitting, it can fail. if the data doesn't have a good signal to noise. So the standard solution of most people is to try to do a Voronoi binning and then run in bins. But this is very problematic because you lose spatial information. So what we did in the past was to use something called Gaussian Markov random fields, which basically provides a way to assume. It's similar to probe the gravitational field from point sources. We try to probe, let's say, the field of the galaxy from discrete information, or from a pixel-based information. And by doing so...
5 minutes. 5 minutes.
Okay, almost done. So by doing that, basically, we can actually preserve, if you see the red arrow, you can actually preserve the original image and even sample in super resolution, which basically changing the paradigm to analyze the data, we are able to preserve the spatial information. So something that we are also developing now is a new technique to decompose galaxies. That's very important to try to decompose out the bulge, the disk, different components, because they are probing different physical processes. And to date, there is no actually silver bullet to try to decompose galaxies from spectra. Again, this is preliminary results, but promising. So I'm developing a new approach for that. So what I show here is the left side is the optical image, which I don't use. I use directly the tensor, but I can extract from the tensor different components that they share similar spectra. And the key point is because the methodology is parallelizable, we can increase the speed by quite a lot. The current state-of-art code takes few hours per galaxy, but because we changed the way how we analyze that, we can run in 3 minutes in CPU, and we are starting to develop a GPU accelerated version, which I hopefully is going to run a few seconds per galaxy, which again, that's the only way to analyze the data, the load we expect in the upcoming years. So to finalize, we are supported now by the Chinese Academy of Science, the National Science Foundation of China. I don't think grant access is a problem here. We have a dedicated GPU workstation. We got also recently a new grant to buy a new one. And okay, I'm not going to bore you with the technical details, but I want to make some advertisements. We are involved in many different projects here, and also with Brazil. So Shao is part of SKA. Some people here just joined Bingo. I think also there are people in JPAS. We are the headquarters of one of the Chinese Space Station Science Center, LAMOS, and many other programs. And we have money to hire people. So if you have any postdoc, anyone that are interested to maybe to consider to apply here, spend a few years, just please let me know. Thank you.
Thanks, Rafael. Right in time. Let's open up for questions. You actually have more time for questions because you stopped 2 minutes before the end of your 25 minutes. So
I have a question for Rafael.
Miguel, go ahead.
So Rafael, the Chinese space telescope is not much discussed in the West. So can you talk a little bit more about it? So how does it compare with James Webb, which is launching? Because you compared it with Hubble, there's a larger field of view. Can you talk a little bit more what kind of frequencies you get? You know?
Yes, I think it's comparable to WFIRST. I think it's very similar to WFIRST. It's not similar to James Webb because James Webb go to near infrared. And for many political reasons that I may not discuss if I'm recorded, but there are problems for China to use near infrared now because of the German. So let's say it's a WFIRST similar, but I don't think it's not going to compete with James Webb because they are actually probing different things.
So it's on optical.
It goes infrared, but not as infrared as red as James Webb. So, okay, but also
the field of view you said is 1 square degree, right?
Yes, yes.
So it's is what? So just trying to get similar.
I don't remember now, but I think it's not so. I think it's similar. They are very similar. They are very similar.
And it's supposed to operate for how long? I know Roger is in line, so last question.
10 years, at least.
Okay.
And the reason they don't discuss, I think it's a China thing. They don't like to discuss before to be done.
No, it's fine anyway, but we have to be prepared as a committee.
Okay.
But they're open to collaborate.
So I will pass the word to Rogério.
Yeah, just to say first that W1 changed its name now. I think it's called Roman Telescope.
That's true. Yes, that's a good point.
And also following up this question of Miguel, what's the timeline for this space telescope?
Well, I mean, technically they should launch by 2024, but I don't trust in this number. I mean, that's the expected date, but I think it's probably going to delay a bit.
Okay, and another question unrelated. Have you tried to find stellar streams with Gaia in our galaxy?
Not yet. I mean, that's one thing I would like to. It's just lack of time, but yeah, that's an interesting project, but I just don't have the manpower.
Thank you, Rafael.
Yeah,
very nice.
that's what all of us need manpower for these things. Too many data, too few people.
Yes.
More questions, everybody? I will join João Braga saying that we are having very few questions here. Who else? Please. No more. So let me ask you a question on the data analysis and the hardware facility. Mariana presented, I guess it was yesterday, the linear stuff for the LSST and the data hub. Are you guys doing something for COIN, working sort of a data hub for this the giant telescopes, the GMT, TMT, and the LSST? You have any plans for that?
For LSST, COIN has one of the how they call? It's not stream. I forgot the name, but yes, we do. We got one. Actually, technically, Emily got for COIN, not exactly for COIN, but I mean, kind of. But because I think they are going to allocate what we can get as data in for different applications, right? I just forgot the name, but yes, we have one related to, but only for LSST.
Is this what is called the Data Access Center, Rafael?
No, it's something. It's just about how, because it's about how they decide, because they cannot store everything they observe, so they need to make decisions on the fly. And actually, the respect is related to that, like how to make some decisions to what we want to store for a particular scientific task. And I think there'll be few. So basically, they're going to make decisions based on what people want. And they open a call. Some people got basically for different tasks what they. So basically, it's based on alert based, right? If you see something that looks of interest, then you download. Otherwise, it's impossible to process. That's the same for SKA. They just are going to throw away most of the data.
Well, I have another question then again to the Chinese telescopes. No one's there. So I still understand. Is it going to operate partially in survey mode, or it's really on project by project basis?
No, it's mostly survey mode, but there will be few project based. But so basically, the survey mode is already kind of it's going to take most of the time, but different instruments then they can do different things because there are at least 4. So the main survey is really survey in the strict sense, but they still need to decide about the deep images and also specific instruments you can make different applications. It's like LAMOS. LAMOS works in a similar way. It's a survey mode, but if I want a particular target, I can ask them to survey the target. The only thing that's going to be public to anyone, but that's okay.
Well, we leave them more if there are more questions, we leave for the paredão at the end of the session. So I'll call now Miguel Quartin for his speech.
Okay. Okay. I think everyone can see it. Let's start.
Yes.
Okay. So thanks, Rogério and the other organizers for the invitation. And I also apologize that I was not able to attend all the sessions, also because of the different time zones and some other constraints. But I'm glad that you guys are reorganizing this event. I think it's interesting. And I've seen some interesting talks. And anyway, so I'm going to talk a bit about some work I have been done in recent years, which is regarding the use of supernovae beyond what they are traditionally being used, and trying to find a different, observable to go to this, reach this goal of precision cosmology that we've been hearing about for many years. And this is work done in collaboration with Luca Mendola, my former students Thiago Castro and Carolina Garcia, and Bruno Moraes and Beatriz Siffert from UFRJ as well. So let's talk a bit about distance in cosmology. I mean, just for a broader audience, maybe the first slide. So, if you are inside the solar system, you can do laser ranging, which is people have been doing, the space agency has been doing for a long time. You can shoot a strong laser in a planet, or, triangulate communications with your satellites and spacecrafts, and then you can measure distance very well in the solar system. If you now go a few orders of magnitude beyond, inside the Milky Way, you can do stellar parallax, and Gaia has been very successful in the last 7 years of measuring distances, and in principle is capable to reach a few kiloparsecs, maybe even 10 kiloparsecs, but you need very precise astrometry. And it's very hard even to go to the other side of the Milky Way with this method. Now, if you go to nearby galaxies, there's been a new observable proposed recently, which is this detached eclipsing binaries, which you can get very good, very tight 1% level precision to the Magellanic clouds, but you cannot, it's still up to debate if you can extend it to Andromeda. Would be nice if you could reach a little bit to Andromeda, and then beyond that, you need to rely on Cepheid variables, right? And then what you want to do in cosmology is to build this Hubble diagram, and to go anywhere beyond 0.04 megaparsec, you need good standard candles, which means something which you have a known intrinsic luminosity, or that you have a known intrinsic size, then you have a standard ruler. And there are two classic standard candles. So if you want these rigorous, standardizable candles in cosmology, one is the Cepheid variable stars, which you can reach only up to redshift 0.01, more or less, not much more than this. And of course, now we have binary neutron stars. So now 3 class. Now is the third one, which is binary neutron star, recently with LIGO. But even though the next run of LIGO should only reach 0.04 in redshift. Of course, this with future next generation gravitational wave instruments, you can even go further. And then type 1a supernovae, you can reach up to redshift order 2, right? Now, both Cepheids and supernovae, they have intrinsic variability. It's not known if the binary neutron stars also have this, but you have empirical relations which allow us to calibrate and standardize them. So this is a classical picture of a kind of type 1a supernovae. We have a white dwarf with a red giant companion, though you could have also 2 white dwarfs. It's another scenario. And so far, then the only proven high Z standard. Every now and then you see discussions about using gamma ray bursts or other kind of astrophysical object to operate as standard candles at very far high redshift. But so far, the only one proven really is supernovae. And you can get to scatter of less than 0.50 magnitude in the Hubble diagram if you have good measurements, especially if you have infrared, even better. But they are arguably subject to many more systematic effects than the baryonic acoustic oscillations, which are mostly linear, not exactly completely, but they are mildly nonlinear only, and the cosmic microwave background, which is very linear. And then the systematic errors are already the dominant part of the supernovae constraints, and we have all the 2000 supernovae in the largest catalogs. Now, in the next 10 years or so, we're going to have an increase in statistics by at least a factor of 100. And it's mostly due to SST, but also due to the Zwicky transit factor. So there's a huge effort needed to improve the understanding of systematics in order to make use of all these extra statistics you're going to have. So as I told you, the SST is expected to detect over 1 million supernovae. The point is, you need spectra of the supernovae, as Rafael was saying, and then you're not going to get spectra of all of them, but they now have, some joint agreements with foremost in order to get over 100,000 spectra. So in any case, you're going to be over 100 improvement on the numbers of supernovae. And in low Z, there's already an instrument which is operating, which is this Palomar Zwicky Transient Facility, which has a field of view of no less than 47 square degrees. So it's completely out of proportion to anything else. It's a huge field of view, so it means it can map the sky very, very fast. Basically the hemisphere, it goes basically the whole sky in a night. It's really amazing fast. And now, okay, supernovae have been traditionally used as a distance probe, therefore a background cosmological probe, but at least two ways in which supernova can be used to measure also cosmic structure. The first one is through supernova lensing, which is not the topic of today's talk, and is what I consider the hard way. And I have been working on this in the past, so I have a number of papers out, and this has been picked up by the community. The Dark Energy Survey has this paper by Macaulay out as well, doing this method. And it's hard because it requires nonlinear modeling, okay? So it has effects on nonlinear structure. And then you have the peculiar velocity correlations of the supernovae, which is something I have more recently turned to. And it's considered easier in the sense because it's linear physics, linear perturbation, basically. And they both methods work even without cross-correlating large-scale structure surveys, but of course you can also cross-correlate. Right, so lensing affects basically distant supernovae, redshift above or the order of 0.4, more or less. And peculiar velocities, on the other hand, affect lower nearby objects. Up to, it could go, if you have very good statistics, maybe up to 0.4. That's what we are proposing, but no, previously only considered below 0.1. And what I mean, peculiar velocity in cosmology means some velocity which is outside of the Hubble flow. So no, something which is added to the homogeneous isotropic expansion. And a typical peculiar velocity today, redshift 0 is order maybe 600 kilometers per second, which is, in terms of speed of light, is 2 parts in 1,000. And this incur an extra blue shift or red shift, depending on the direction that you have to take into account. Now, the point is that very low Z, they are very large perturbations, so not very important. But the most important point is that these velocities are not random. They are correlated. Now, from linear theory in cosmology, we understand from the linear method power spectrum how these correlations behave. And we can measure them and then therefore infer the information on the power spectrum, what is the real cosmological power spectrum behind this. So basically the idea is that, if there are two supernovae which are nearby in the sky, they should have correlated velocities. And the velocity correlation is long reach. So actually, when I say nearby, this is a relative term. They do not have to be near in any, even in cosmological sense. They can be actually quite far apart, but the closer they are, the higher the correlation. And part of the Hubble residual diagram, which is what is left over from the Hubble diagram when you subtract the background cosmology, should not be random anymore and not uncorrelated and independent. And you can build a two-point correlation function to relate the velocity of the supernovae, which are, again, not so far from one another. So, if you have a supernovae, which is, compared to the Hubble flow receding from you, supernovae which are in the same region have an excess probability of also being receding. If the supernova is going towards you, supernovae in the same region has an excess probability of also going towards you. And this correlation is proportional, for instance, to the amplitude of the matter power spectrum, or if you want, proportional to sigma 8. So this was originally proposed, some 14 years ago by Gordon Landers-Loza, and then we picked up this in 2015 with my former student, Thiago Castro, which is here in the picture, and revisited this idea. Now, so to get some intuition, this is just some simulations here of the Hubble residual diagram. So that's the Hubble diagram after I remove the background expansion, and I'm only going to 0.1 where the velocity is higher. And this is just a small degree in the sky where I have, ideal supernovae, which means no intrinsic dispersion. Again, just to illustrate. So there you see that, this is one realization. You see, this is not a random distribution around zero, right? You can clearly see here that all objects are correlated because they are all above. So you have one object above, it pulls all the other if you want. Now you have one guy below and pulls all the other one below. So you see there's this effect. If I do a different realization, things look different. So you're not going to try to fit any template to this distribution. Basically, what we're trying to find is just how correlated they are. Okay. And now if I put the supernova dispersion by eye, these things look harder to see, but the information is there. You just need now a nice statistical estimator that is able to recover this. So it's still measurable, even if you add the normal expected supernova distribution. So let's talk a bit about spectra. Some equations here. I hope it doesn't scare you if you're not familiar, but I'll just go through it. So I'm just saying that the velocity, when we mean velocity in cosmology, we mean radial velocity. It's very hard to measure transversal velocity because the Doppler effect is order squared, But the radial velocity is what affects the redshift directly. So the normal power spectrum of the delta, the density contrast, is what people usually talk about when they talk about galaxy distribution, measuring clustering, etc. Has this kind of shape here. So the PMM is the primordial cosmological spectra. But what you observe had lots of different effects. I didn't even put short noise here. I forgot. I should have put short noise. But then you have the growth function, which means how things are growing in redshift. This is okay understood. Then you have, this is smoothing function here. This is nonlinear redshift space distortion. I discuss in a second. Then you have the famigerated bias, the thing that people have been struggling to understand and model because it's directly proportional to the spectrum, which is the bias of your tracer, whatever the galaxy you're using. And then you have this term here in front, which is the redshift space distortion. I'm going to go back to this in a moment. But if you just go to the velocity spectra, they look different. The most important thing that you should notice is there's no bias here. There's no B, it's a bias, and no beta, which is also dependent on the bias. It doesn't appear here. So the velocity is independent of the bias. So it means that you measuring together velocity and density, you are less degenerate with this bias, which is this thing which is for a cosmologist is a nuisance parameter. Okay, and then what people usually do is try to decompose this in a monopole, quadrupole, and an hexadecupole part. Again, I'm going to skip this part, but it's just that it's true that the hexadecupole part of the delta is also not there's no bias in it, but this is hard to measure. Though. It's very hard to measure. So the velocity also helps with this hexadecupole thing. Anyway, this is a more technical point. Let's go back to the distribution. So this is an old supernovae catalog from some 6-7 years ago. Now we have kind of double the number of objects in the recent Pantheon catalog of last week. But anyway, this is in galactic coordinates as we cosmology like, which means the galaxy is here in the equator. Then there's a sim dipole, but forget about this for a moment. And these are the supernovae of this catalog. So you see, you have low redshift supernovae, which are everywhere. And then you have this stripe 82 of SDSS. But this plot is hard to see because there's no redshift information. So now let's open this up in redshift space. So now I have a third dimension, which is redshift space. So now I'm doing this galactic projection, but also adding redshift information. Then you see that all of this JLA catalog has only 4 narrow pencil beams of high redshift supernovae. So they only observe, a tiny fraction of the sky. So you see, you can populate this with many more objects in the future. And so it's only 4 small pencil beams, really. Now, these correlations from peculiar velocity, they are linear, right? So therefore, this is power spectrum. Understand these equations, even if you're not familiar, it's just linear perturbation. Now, what we did in this JLA catalog is to try to analyze it and recover the information, the real data. So we did a 14-dimensional MCMC with 6 cosmological parameters: the baryonic density, the cold dark matter density, Hubble constant, amplitude of the fluctuations, NS, the slope of the power spectrum. This gamma parameter, which is a parameter which is not present in lambdas in normal GR, is an extra parameter for modified gravity. And then you have nuisance parameters for us. Okay, I'm not going to go in detail. So it's just trying to be very robust. And what we get is here. So lensing, I'm not explaining today in the seminar, but the peculiar velocity is the green contours. So we are adding this peculiar velocity and lensing, all using only supernovae data, nothing else. And the combined is the orange. So you see, it's still, the current data is still very degenerate. This is the gamma parameter means as you go up in this gamma parameter, the structures is growing slower, and you go down, it's growing faster. And the GR is really 0.55, which is right here, this black line. And so what you see from Planck, or you expect, at least from the GR and normal data, is something around the star. So constraints are degenerate, but again, if you marginalize over the parameters, you are measuring sigma 8 with the, if you want, assuming GR, you measure sigma 8 in this brown curve, which is, it means that the supernova is detecting sigma 8, it's not 0, right? 0 is ruled out. So it's already detecting that you have correlations there because of peculiar velocity. Okay, and the gamma parameter is still very degenerate, but it's going to improve a lot in the future. So I'm going to skip this. It's just to say that we can measure all the parameters together. So now if you compare to other data, current data, this is what you get from galaxies, clusters, and the CMB. So just take a look at the CMB, which is people are more familiar with. This is Planck year 1, 2013 data. Sorry, and you can see even though the supernovae contours are much broader and much less constraining, it's very good to have complementary probes because it's already excluding 2/3 of the CMB region, right? So again, even if your observable is not so precise, just because it's orthogonal, there's different degeneracies, you can combine to very good gains with other surveys like here, the CMB. So that's very interesting. Now, we also wanted to do more realistic peculiar velocity forecasts. So, wanted to understand how this change with different survey parameters for the future, the area, the depth, the number density of objects. So it's much simpler to do analysis using a Fisher matrix test, so Fisher matrix method. So this is a Fisher matrix of the power spectrum, looks like this. Now, if you have velocities, it's very similar to the normal galactic Fisher matrix. It's just that instead of 1/n here, for those who have seen this before, you have a different. Now we have this sigma v squared, which has to do with how precise you can measure the distance, right? So a better measure of distance gets the smaller sigma v effect here, which has to do with this velocity dispersion. So we do this Fisher matrix analysis. So this is I did my former master's student Carolina, which is now in Florida. And then we try to estimate what happens for the LSST in this wiki. So you see this wiki, this is theoretical completeness curves at maximum. I mean, if the wiki perform ideally, just take into account the depth it can reach, it can go to redshift 0.2 or so, right? It can really be complete there. Now, the LSST can go to high redshifts, but then it depends a lot on the strategy, right? Because some of the strategies proposed for LSST does not have high enough cadency, so you lose lots of objects. So we ran full analysis on one of these proposed strategies for supernovae with LSST, and we got this completeness curve for supernovae, which is here, which means that you're getting around 10% of all the supernovae in the LSST area. So we still can lots of room to improve. There's just the detection, not even the follow-up, but detection with at least a number of filters, so you can classify them as quickly as candidates of type 1A. So LSST collaboration has been discussing a lot how to improve this, and they should be able to improve at least in the low redshift. So we also did an estimate assuming 20% overall, which is, I think, realistic. It can be done. Anyway, so this heavy slide, so let's go slow. So we can also make model-independent measurements of this clustering. So what people do in cosmology, usually when they talk about full shape or BAO measurements in general, using all the modes, is to assume a given parametrization, which means you put parameters for your background cosmology, for your dark energy, for instance, and some parameters for your perturbation analysis could be the normal lambda CDM parameters, or you can put some extra parameters, for instance, for modified gravity, as I was showing there. But you can do some things without assuming any parametrization by using a combination of the Alcock-Paczynski and Kaiser effects, which I'm going to explain next slide. But then you can do model-independent constraints. And in particular, we showed that we can constrain, for instance, the Hubble flow, which is h of z, not h of z directly. It has to be h of z over h naught, because you cannot measure h naught with this method. But you can measure this Hubble flow measurement of h. And there are very few model-independent observers of h, which is interesting because people are now trying to have some tensions in LSTM. What's the origin? It's good to have model-independent measurements. So radial BAO is sometimes advertised as model-independent measurements of h, but actually measures h times rs. So it's a multiplication of h with the sound horizon that drag epoch. And now people have been discussing a lot some scenarios that changes the early cosmology because of the Hubble tension. So people have early dark energy models have really risen in popularity. So therefore, it means that if you're doing something different in the drag epoch, this measurement will change. So they're not, no, they have this model dependence on the drag epoch.
5 minutes, Miguel.
Okay, thanks. This redshift drift has been proposed, and I also have been working on this, which is measuring very accurate redshifts with extremely large telescopes, like Roderick was talking yesterday. But you need lots of time in these extremely large telescopes, so it's not really easy to do. And cosmic chronometers has also been appearing a lot in the literature, but they rely on the astrophysical modeling of passive galaxies and population synthesis simulation. So it's also some model there. It's not completely direct. So the Kaiser effect is due to the linear collapse of structure. So gravity attracts everyone, and structure becomes more and more linear as the universe evolves. So we have infall of matter in large potentials, and this creates distortion in redshift space. So something which is spherical in real space appears elongated and ellipsoid or pancake-like, sometimes not in redshift space along the line of sight. Right? You also have nonlinear effects when you get to small scales because the velocities become nonlinear, and this creates an elongation very close, and nearby in the smaller scales, which are called fingers of God because they point. They distort things along the line of sight. So you have this combination of Kaiser and fingers of God. The Kaiser is linear, you can model. Fingers of God is harder to model. You also have the Alcock-Paczynski effect, which is not drawn here, which means spheres are just mapping to different spheres with different radii. And that is because you have to assume a cosmology in order to convert angles into wavelengths. And if you do it if you're mistaken on your cosmological background model, you're going to mistake on this conversion. It means that what you think is a sphere of a different size. So this is the Alcock-Paczynski effect, is well known, and you can combine them to do this model independent clustering. So we combine the supernova velocities and supernova positions to make this combination. You get good precision and both, in this H. So you can measure H in different redshift beams. Just take the last column here. You can measure it to less than 10% in different beams, which is interesting enough because it's model independent. You can also measure the P the power spec directly without making any assumption on the early universe. You just, it's going to come from the data this way. Now, if you scale with the number density of objects, then this is also very far from the cosmic variance limited because these errors just keep on shrinking, even though you add more and more objects. So SST is expected to be in these black dots here for the different redshift beams. But if you even go 10 times more objects than SST, you're still going to get information. This does not happen for galaxies. For galaxies, if you go 10 times more than SST, it doesn't matter because you're already cosmic variance limited. You really limit, you're not gaining any cosmological information. Now, the fact that, the velocity does not depend on the bias means that adding density and velocity increases the signal. So you can add this P delta delta and the cross term P delta V, and you can constrain better both cosmological and bias parameters. And this method we refer as a 3 times 2 point because it really uses 3 power spectra, PVV, P delta delta, P delta V, density, velocity, and cross. And 3 times 2 point, galaxies and supernovae. Now, the supernova, as I said, can also density. You have lots of supernovae with SST. This is a different tracer of density. So then you can do a similar thing to a multi-tracer analysis with the supernova and galaxies. So we can then use both supernova and galaxies to measure all these delta and V's, and then you get 6 power spectra. Okay, and this is the method we proposed recently, the 6 times 2 point, which is using really all 6 spectra. So I'm going to just show you a huge equation to scare you, but basically the point is you have galaxy, supernovae, galaxy, supernovae, then galaxy velocity, supernova velocity, velocity. And this is in principle all understood, except that you have now one bias for the galaxy, which is unknown, and one bias for the supernova, which is also unknown. So you have lots of parameters nuisance parameters to marginalize over. So what we get, assuming a foremost-like spectroscopic survey, which is 7,500 square degrees, plus SST supernovae, and 15% completeness, even less than before. And then we put lots of nuisance parameters, one bias parameter for galaxy and one for supernova for each redshift beam. So we have been very general here, but still the method can work well. So here I show you for different redshift beam, first, second, third, and fourth beam. So each beam on itself is very degenerate on this gamma sigma 8, but they are slightly different inclinations. You combine them all, you get these contours here. So let me go step by step. The blue is what people usually do, only using galaxies. The magenta are adding supernova velocities. And the orange is adding supernova velocities and supernovae clustering. So you can really go from blue to the orange with LSST, which is a large improvement. And again, the same CMB constraints for today. This is not forecast for this is forecast for the future, but the CMB is real data. So then you can combine the CMB and the best estimate and get these nice green tight contours here. Okay. So I have numbers here, but the point is you have similar precision to the CMB using TTT-EEE for those who are in the know. And you can combine the CMB with the 6x2 to get factor 5 improvements in all 5 parameters here. Consider sigma 8, gamma, H, omega meter, omega K. So, you get constraints like 0.1, 0.2 in sigma 8 and gamma, 0.04 in A. So this is 8.7, in our fiducial model. This is the Hubble constant, which is our intention. This is 100 times less than what may be using. So 70 means for me 0.7. So you get constraints, we have different tests, but the CMB is here, and the combine is really 5 times better in all parameters. So again, the power of combining different probes. Okay, you can also measure the background parameters, but I'm running out of time. And the 6x2 point approach is not only more precise, it's more accurate. So it means less chance of having systematics because you can measure the bias much better. So here are the measurements of the bias forecasted, of course, for different beams. So the dotted line is just using galaxies. The dashed line is using galaxy and supernova velocity, and the thick line is using galaxy, supernova velocity, supernova clustering. So really, get tighter measurements of bias, which means, if you're doing some wrong modeling of the bias, it's a larger chance you can catch up that in the data, right? So you don't get wrong results. This has been also picked up by other people in the community. So Howlett et al. And Alex Kim has been also working on this. They made also forecasts in a couple years ago using LSST with supernova galaxies, similar to what we are doing, but they were constraining this F sigma 8 parameter, which is a different way of constraining this sigma 8 and gamma. So you have one F sigma 8 per beam, and they did these constraints for LSST, different assumptions. You can get these red dots here, and they have different curves for different gamma. So what you expect from GI is blue, but then you can rule out the pink and green. That's what they're trying to show here.
Time is over, Miguel.
Okay, so I think time is over. So the conclusions are here.
Yeah.
So I leave you with the conclusion. I think I talked all about this before. I just end with the last phrase that, usually, both lensing, which I didn't explain here much, and the peculiar velocity, I consider usually noise in the supernovae data. I'm just saying, don't throw away the noise. You should recycle it and use as information. Thank you.
Thanks, Miguel. Since we are going for the break, I suggest that we have at most 2 questions and then leave the other ones for the paredão later on. Anyone?
I have a question.
Okay, I see Mariana with her hand, and then Marcos. Mariana, please.
Thank you, Alex. Miguel, really nice talk. Thank you. And I was wondering, the velocity you are considering is the velocity from supernovae. And I was wondering something like the halo model, because you have the distribution of the galaxies, so you compute the galaxy power spectrum. Do you think could we get more information if we consider the one halo, let's say one halo and 2 halo term, the signal from the hosting galaxy with the supernovae, this sorry. So the one halo term in this sense would be we get some information of the correlation between the galaxy which is hosting a specific supernovae, and the correlation between this hosting the supernova with another galaxy, with a distance galaxy, let's say. But I believe this power spectrum is taking into account all these, so, given the different scales.
So thanks for the question, man. I'll try to answer it. So here we are not going to the nonlinear regime on purpose to be very safe. So we are stopping at K of 0.1 in all these forecasts. So we are stopping K.1.
Oh, okay.
We are safe from this halo model modeling. Now, it's true that if you go to higher K, in principle, there's lots of information there. You can gain many more modes, improve a lot your constraints. But then you have to be careful about nonlinearities and the halo modeling, right? So we are really thinking at the moment now, what's the largest K that we can go and still not be biased, be robust. So this is still ongoing research. I don't know the answer at the moment, but if you can go to higher Ks, you can improve. And then you have to wonder about this and test with halo model or using effect field theory of the LSS or some other, smart scheme to handle these things. Now, let me just point out, there was a paper came out a couple of years ago by Benjamin Van Delt and Mukherjee, which they were doing something very similar to what you discussed. I can give you the reference later, which is really trying to constrain the fact that you can have a galaxy and a supernova. You have two maps, but the galaxies and the supernova must come from one of these galaxies. So trying to just make the maps touch. All the supernovas should match one of the galaxies. It's a different way to find these constraints. It's they write things in a different way, so it's hard to make a bridge between our method and theirs. But it's similar to what you're discussing, and it looks promising. It's a different way of analyzing it.
Nice. In the velocity, I believe the velocity of the supernova takes into account the intrinsic velocity of the galaxy.
So,
or no?
Yeah. So the velocity field should be for all matter, right? So there are no biases.
Okay.
Gravitational is universal, so everything is following the same potential, right? So you do have, what you have is you have a nonlinear term of the velocity. For instance, the stars are orbiting the galaxy. They are in the spiral arm. They have this 300 kilometers per second order of magnitude around the galaxy, and this is completely nonlinear and unmodelable. You don't know which part of the spiral arm the supernova is. So you put a stochastic velocity term to account for these nonlinearities, but it's not very relevant at all. In the if you can put this even large, and we tested it, it doesn't change much.
Oh, great. Thank you, Alan. Miguel.
Okay. Marcus, you raised the hand.
I think it was Laerte, no? I don't know.
Was Laerte? I think it was Marcus Meyer. Was it Laerte?
I think it was Laerte.
Yeah, Laerte, I think, asked something.
Okay. Go ahead, Laerte. I don't see you here, but
I think it's on the video, and the mic asked something, then disappeared.
I think he's gone. If he's not, I suggest that we go for the break. We reconvene in 25 minutes. Time to brew a coffee, have the coffee, and come back.
Okay.
All right. See you in 25 minutes.